Imani, and through the miracle of time travel, the ICFP organizers are always listening to audience feedback. You want to hear about continuations in verification frameworks? Here's the next talk for you. As a bonus, it also handles concurrency.
All right, thanks. So this is a joint work with Lars Bickertl. Yes. All right, so we want, in this talk, we want to discuss verifying programs with continuations and concurrency, two features that are both known to be challenging to handle, to reason about. And we have some objectives in this project. One is that you want to reason context locally. Well, when you have continuations in a programming language, close. Yes. Is it better now? Is it? Okay. So when you have continuations in your language, well, you have to, when you want to prove something about your programs, you have to consider whole programs, right? Because the continuation, the rest of the program can be captured, or something can happen to it in general. And well, you need to reason about whole programs. That's what we call non-context locality. We want to reason context locally for the parts of the program that do not behave non-context locally. Let's say it that way. And we want to verify correctness of programs. We want to set up logical relations, improve contextual refinements of programs. And one other objective was to implement, to prove correctness of implementation of cooperative concurrency with continuations, something that is quite well known. Another criteria for us was to get these proofs at a high enough level of abstraction that they are actually simple enough to mechanize. And in fact, we have done this. Everything that I present here and is in the paper is formalized in COP. So let's look at a very simple motivating example. Let's think of web servers. Well, in a web server, when a client makes a request, the web server has to respond, but it has to also take into account what has happened in the past, the history of communication with the client. Now, in this aspect, we can think of two different styles of programming the server. One is that the server actually stores some information about this past interaction, and when the returning client comes, uses that information to respond. The other is that whenever the server is actually sending something to the client, it can take the continuation of the program running on the server, store it, and whenever the client comes back, can just start running the continuation again, right? And we prove actually that these two styles of writing the server are actually equivalent by showing that two simple implementations of two servers in these two styles are equivalent. And notice that in this example that I described here, there are already some interesting features and interesting things happening. There is concurrency because each incoming request is actually handled by a different thread. And we have continuations, and we actually store continuations in memory, so we have a higher order heap. And for this project, we are working in the iris program logic for two reasons mainly. One is that it has already been shown that it can handle the kind of reasoning that we want to do here. And also that the formalization of iris in Coq allows us to formalize the results that we have. But there is nothing really specific about iris. And if you have any program logic that has the advanced features that iris has, you can employ it to do the same kind of reasoning. All right, let's look at the programming language that we consider. It's a variant of System F with recursive types, higher order references. Again, you can store codes as in continuations or functions in memory. You have concurrency and you have continuations. Right? Everything here, the typing rules, syntax, semantics, it's all standard, but just to show you some things that we know what we're talking about and agree on the syntax, we rewrite this kind of cont tau for the type of continuations that accept a term of type tau, and we can go back to that point with giving it a term of type tau. And we write cont with this blue cont for the captured continuation, which is just an evaluation context. And we write callcc and throw like that, and here x in callcc is the binder for the captured continuation. And an evaluation context is basically what determines what what point of execution we are at in a program, right? We have the empty context, that is if we are running the top-level program, and if we have an application, this is a call by value language, so we first evaluate, determine the function position, and when that's a value, we continue with the term in the argument position, and well, in an if then else, we start by evaluating the condition, and so on, right? And we define the operational semantics in 2 steps, basically. We define a head reduction, which is annotated with some evaluation context. And well, the only interesting case where the evaluation context is being used is the case of call CC, because it is capturing it, right? And for our machine, where we have a thread pool, a number of threads that are running concurrently, well, the machine takes a step if one of the threads takes ahead a step under some context, or if one of the threads is actually doing a throw operation, in which case we forget about the continuation and we continue with the captured object. The typing rules are again standard. We use 2 typing contexts, one for term level variables and one for type level variables. And things like, so we annotate the polymorphic terms with this capital lambda. So for example, if you look at this typing rule, capital lambda E is of type for all alpha tau, if E is of type tau under the assumption that alpha is a free type variable. If you have a term of type tau, you can allocate it and get a reference. In order to type check a call CC, well, you have to type check the body under the assumption that the variable x is bound to the continuation object that is of the appropriate type. And whenever you have a continuation object and a term of the appropriate type, you can just go back to that point. And because we never return from a throw operation, it can have any type. Right? This is all standard. All right, so now about program verification. We're using weakest preconditions. This is something that we've seen in previous talks. This is essentially defined in terms of the operational semantics here, but that's not important. What it means to have the weakest precondition actually hold is that, well, E is safe, and if it terminates to a value, the postcondition will hold for that value. Right? Now let's look at a number of rules that we have. We have inference rules to use to prove correctness of programs. Right? These are more or less a standard, except for the fact that everywhere we have this context K around, right? Because now we have to reason about whole programs, right? So, well, for the case of a value, it's trivial to prove a weakest precondition of a value. The postcondition should hold. For a fork operation, well, we have to show that the program that we are forking is actually safe, and actually the rest of the program can continue with the unit value, which is the result of forking in our case. Notice how here we are reasoning completely modularly with respect to concurrency, with respect to threads that we are forking. We're not reasoning about interleaving of threads or anything like that. We just prove that the program that you're forking is safe and that you can continue safely. That's enough, right? But we cannot do the same with contexts, with evaluation contexts. So, and this happens everywhere. And essentially the reason for this, for having this continuation, for this evaluation context around explicitly is because of the 2 rules at the bottom for call CC and throw. They very closely mimic the operational semantics. And what you see is that in the case of call CC, it is captured. In the case of throw, well, it is thrown away, right? And this is essentially why we need to have this. So let's look more closely at this situation. We have 2 kinds of programming languages. We have context-local programming languages and non-context-local programming languages like ours, where we have a kind of continuations, right? And the style of rules, if we want to contrast the 2, is that with one we have to reason about whole programs, and the other we can just reason about parts of the programs, right? And the reason why we can do that is because of the bind rule, right? This bind rule tells us that if you want to verify program E under some context K, it suffices to verify that program E is safe and that you can continue with any value that satisfies a post condition for E, right? But unfortunately, we cannot do this. We cannot have this in our system. So what we do is we introduce context-local weakest preconditions that allow us to reason context locally. And our methodology here is that we want to specify programs with weakest preconditions, the ordinary ones that we have seen, and basically combine the two reasoning principles and reason about the most of the program that is actually behaving context locally. So let's see how we do this. This is a definition of context local weakest preconditions. Essentially, what this definition is saying is that the E is context locally safe, basically, if it is safe under any compatible context, right? If you want to think about it differently, E is safe and the bind rule holds, right? And this is exactly what it captures. So now let's go back to the situation that we had before. For a non-context local programming language, if we now start using context local reasoning principles, well, we get exactly the same style of rules that we would get for a context local language, right? Including the bind rule. The only caveat is that obviously you cannot get rules for non-context local primitives, call, cc, and throw here. All right, so now what? We have these two different calculi for reasoning about programs, context local weakest preconditions and weakest preconditions. One allows us to reason context locally, but not for call, cc, and throw. And one allows us to reason about everything, but there is no bind rule. But we can mix the two, right? If we want to prove that program E is safe under a context K, and we know that E is context local, well, we can apply the bind rule anyway, right? We can just assume that E does not tamper with the context, kind of by definition of context local weakest precondition, right? And this rule basically allows us to achieve the goal that we had before, that we want to mix the two and reason as much as possible context locally. Right, so this brings me to the next part of the talk about contextual refinement, which is the standard for comparing programs, right? We write it like this. We say E contextually refines E prime of type tau. If for any context, think any program with a whole, if you plug in E and the result terminates, then so should E prime, right? And this condition is actually a lot stronger than it meets the eye at first. It is actually that any behavior that E shows, you should also be able to observe from E prime, right? Because otherwise you would distinguish the two and terminate in one case and not terminate in the other case and violate the property. And for that reason, we actually refer to the left-hand side of the refinement as the implementation side and the right-hand side as the specification side. And contextual equivalence is just basically two-sided refinement. Obviously, proving contextual refinement and equivalence directly is not really something that is easy to do because we cannot really reason about all programs, right? The usual methodology is to use logical relations. We define a relation that is easier to work with and that implies the contextual refinement relation. And this is what we do. We actually define our logical relations on top of Iris, the system that we're working in, and we use the weakest preconditions that we saw before to basically define a relation that we call observational refinement relation on whole closed programs. We have to reason about whole programs. And this refinement relation basically says if E terminates, then so does E prime. And then we use the idea of orthogonality to lift this relation on whole closed programs to arbitrary evaluation contexts and arbitrary expressions, and then define our logical reason in terms of those. And orthogonality is something that is quite well known in the context of logical relations methods. This is basically a way of defining logical relations in a continuation passing style, if you will. And this is the reason why we use it here. All right, if we think about, if we go back to the example that we had, the servers, we actually proved that the two servers are actually equivalent, the two styles of the servers, and most of the reasoning happens context locally. Most of the reasoning is about relating the two tables that are holding the association between users and the data corresponding to each server, and that we do context locally. Okay, to the third part of the talk about correctness of implementing cooperative concurrency with continuations. This is something that is quite well known, has been for a very long time, and here we prove it formally. One thing when you think about this problem is how do we even state it? What does it mean to implement cooperative concurrency correctly? The way we approach this problem is we borrow an idea from compiler correctness, and we define a programming language with cooperative concurrency. I will explain what that is. And a programming language with no concurrency, a sequential programming language that has call CC. And we give a translation, and we show that the translation is correct. Okay, what do I mean by cooperative programming language? This is a programming language very similar to the language we had before. It has a C fork, a cooperative forking operation, and a yield operation. And the operational semantics, just like before, we have a thread pool, but we also have a current running thread that we keep track of. And we keep running that thread until that thread calls the yield operation, in which case we switch to another thread, keep running that one until that one yields, and so on. Right? And if the current thread that is running terminates, well, the whole program terminates. That is our programming language, the cooperative programming language. And we give a very simple translation. We take a very simple implementation of a thread library using continuations that gives us two functions, fork and yield, which we denote with this f and y. And then the translation is basically going through the whole program and replacing C, fork, and yield with calls of these functions. And what we show is that if you have a closed program in the cooperative language, and the translation terminates in the sequential language, then so does the original program in the cooperative language. And you should think of the implementation specification argument that we had before for contextual refinement. So this compilation is actually the implementation of the original program. And the theorem that I just showed you basically follows from the fundamental theorem of the cross-language logical relations, which is morally very close to the logical relations that we had before. The main big change here is that we define a cross-language observational refinement relation now that talks about two programs of the two different languages and what you expect. If the sequential one terminates, so does the cooperative one. And with that, I thank you. There are a number of things that I didn't get to talk about in this talk that are in the paper and in our formalization. Please take a look. Thank you.
Okay, let's start with a Slido question. You showed us some examples with a separating implication. You didn't talk too much about separation logic, which is known for making it easy to reason modularly about state.
Right.
You give us a new kind of modularity. Anonymous wonders, can it be viewed as separation in some sense, since you do seem to be building on separation logic?
In the formal sense, no, because there is no resource that we are actually keeping track of and using the separation conjunction to do that. But conceptually, kind of yes. But yeah, let's take from it whatever you will.
Any direct out loud questions? Yes.
Why call CC and throw rather than, say, delimited control?
No real particular reason. I mean, all the things that I described here can be applied to all those other control operators as well. We simply didn't do it. But for those control operators, I would say that you can probably drive some stronger inference rules. That it's future work.
Another Slido question. Slide 17 says most of the spec is context local. Which parts are not?
Well, the parts that are actually using, let me remember, okay. The parts that are using call CC and throw, right? The one that, when you define this fork operation, you're taking a continuation and storing it, right? Taking the continuation, well, you cannot do it context locally, but storing the operations on the queue that is used internally in the library for storing these things, that is verified context locally, right?
Any other direct out loud spoken questions? Okay, we have another one queued up here, which is basically about the fact that things work out well in your framework when you have a nice nesting structure. It's actually sort of similar to the one in one slide of Andre's talk, where you have the let's see, you need a particular nesting relation between the context local and non-context local reasoning kinds to get the most benefit of your framework. If you just keep switching back and forth between those, your proof probably isn't as nice. Does this tend to infect more of your proof with the less local reasoning form than you would like? Or what kind of design patterns protect against that?
Right. I don't have a really good answer for this because in all the examples that we verified and used, well, it was the case that it was really in 2 levels. So we didn't have anything that would go in multiple levels. But one thing to notice is that this context-local specification, context-local because precondition, is a semantic criterion. And so, there are indeed programs that have call CC and throw, but you can still give them context-local specifications. There are examples of this, and you have one in the paper.
For instance, if you took your thread library and used it with client code that was itself allowed to invoke call CC directly, right, would you still be able to maintain the nice modularity of the proof?
I think so.
Okay.
I think so, yeah. And here the program node has call CC, right? Both the target and source have call CC.
I see.
Yeah.
Thank you.
Yes.
I'll shout it up. No.
Oh, okay.
So how do you prove context locality, and can that sometimes be hard? Like proving that something is context local, can that also be on its own a hard proof obligation, and how do you prove it?
Well, you have, as I showed here, you have these basic rules for working with context-local weakest preconditions directly, right? So you don't need to actually prove that something is context-local, unless if it actually explicitly is using call CC and throw. In that case, you have to open the definition of context-local weakest preconditions and reason at the level of weakest preconditions.
Right. So it's with respect to the semantics, not with rules.
Yes.
Okay.
Okay, let's thank Amin.